Welcome back to the deep dive. Today we're shifting gears a bit.
Definitely shifting gears.
Yeah, usually when we talk about smartphones and
Yeah.
specifically iPhone, we focus on the user interface.
Right, the shiny stuff.
Exactly, the shiny stuff, the refresh rate of the screen or the megapixels in the camera, or just how fast the new iOS feels.
Which is what everyone notices first, to be fair.
Of course. But today we're completely ignoring the screen. We're ignoring the case. We're going straight into the microscopic city that basically lives underneath the glass.
It really is a city. I think that's probably the best analogy you could use.
You think so?
Oh, absolutely. I mean, when you looked at the technical documentation and the engineering schematics we've pulled for this deep dive, you stop seeing a phone. You start seeing a metropolis.
A very densely populated one. So for everyone listening, our mission here isn't to teach you how to change a battery.
No, definitely not.
There are a million YouTube videos for that. We want to understand the engineering philosophy. We're looking at the internal logic board architecture based on actual component-level diagnostic notes.
Right. We want to get into the weeds of the communication protocols that fire in nanoseconds.
And the catastrophic failures that turn a $1,000 device into a paperweight. Because sometimes the difference between a working phone and a brick is literally a microscopic crack in a solder ball.
Or a single line of corrupted calibration data. That's the wild part. Modern repair is becoming way less about screwdrivers and much more about data preservation and voltage analysis.
So let's set the scene here. You've got this stack of schematics in front of you. The first thing that really jumps out from the source material is the sheer density of these boards.
It's staggering.
We're talking about the A-series chips, the A15 Bionic, the A16 Bionic. To the marketing department, these are just, fast processors.
Yeah.
But to a hardware engineer, what are they?
To an engineer, they are a massive BGA challenge. Yeah, BGA stands for Ball Grid Array. It's the mounting method for almost all high-end silicon today.
I really want to drill down on BGA because reading through the sources, it seems to be the root cause of so many issues.
Oh, it is.
Because in the old days of desktop computers, you had a CPU with little gold legs, the pins, and you just drop it into a socket.
Right, it was totally mechanical. Just plug and play.
But in a mobile device, I guess space is the enemy.
Exactly. You can't afford the vertical space for sockets. So BGA puts the connection points entirely underneath the chip itself.
Paint a picture of that for us.
Sure. So imagine a grid of 1,000 tiny copper pads on the very bottom of the processor. You take 1,000 microscopic spheres of solder, literally tiny metal balls, and place them on those pads.
1,000 of them.
Easily. And then you heat the whole thing up.
So the chip is literally floating on a bed of molten metal for a few seconds until it cools and solidifies.
That's exactly it. It's the surface tension of the liquid solder that actually holds it perfectly in place.
That sounds incredibly fragile.
Well, here's the problem physics. The logic board itself is made of fiberglass and copper, right? But the chip is made of silicon.
Okay.
When your phone gets hot, like when you're gaming heavily or fast charging, those materials expand. But they expand at totally different rates.
Oh, the thermal expansion. So the board is stretching one way and the chip is stretching another.
Precisely. And what takes all that physical stress?
Those tiny solder balls underneath.
Right. Over time, or especially if you drop the phone and the board physically flexes, those balls can crack. They just shear right off.
Wow.
And because they are hidden completely underneath the chip, you can't even see the break.
Which brings us to the repair terminology found in the documentation. I kept seeing the terms reflow versus reball.
Ah, yes, the great debate.
I see reflow mentioned a lot in amateur repair forums as a sort of quick fix.
It is a quick fix and, frankly, usually a bad one.
Why is that?
Well, reflow basically means you just blast the top of the chip with hot air, hoping to melt the solder underneath just enough that the crack magically heals itself.
Kind of like kicking a jukebox to make it work.
That is the perfect analogy. It's exactly like that. It might reconnect the joint temporarily, but the exposed solder is already oxidized. It will fail again. It's just a matter of time.
Whereas reballing sounds like microscopic surgery.
It absolutely is. Reballing is the actual professional standard here. You have to desolder the chip entirely, lift it off the board, clean off all the old solder from both the chip and the board using a copper wick.
That sounds tedious.
Yeah, very. And then you use a specialized metal stencil to apply fresh solder paste perfectly onto those 1,000 tiny pads. You are essentially remanufacturing the connection by hand.
And what's the margin for error there?
Zero. Literally zero. If you overheat the chip during removal, you kill the silicon die. If you misalign the stencil by a fraction of a millimeter, you bridge two pads together and create a dead short circuit.
You really need a steady hand for that.
A steady hand and a very deep understanding of thermal profiles. You can't just guess.
Speaking of short circuits, the notes mention a specific failure mode that seems to be the nightmare scenario for technicians. A short on VDD main.
Ah, yes. VDD main. If the CPU is the brain of the phone, VDD main is the aorta.
The aorta.
Yeah, it stands for the main voltage drain line. It is the primary power rail that directly connects the battery to almost every single major subsystem in the phone.
So it's the main highway for all the electricity.
Correct. The second you plug in your battery power, floods into VDD main. From there, it branches out to the display, the audio amps, the cameras, everything.
Okay.
Now imagine one tiny capacitor, a component the size of a grain of sand, fails on that main line.
And by fails, you mean it breaks internally and connects the positive line directly to the ground.
Exactly. It creates a path of least resistance. So all that electricity from the battery ignores the CPU, ignores the screen, and just rushes through that one broken capacitor straight to ground.
And the phone just dies.
Instantly. The phone goes totally dead. It won't boot, it won't charge. Though, if you have a thermal camera, you'll actually see that one tiny spot glowing, white hot.
So when a listener's phone just randomly dies one day and absolutely won't turn on, it's not necessarily a broken screen or a degraded battery.
Not at all.
It could just be a single ceramic capacitor causing a massive traffic jam on the main power highway.
That is actually the most common cause of sudden death in modern iPhones. And finding that one bad component among thousands on a multi-layer board is where the real art of diagnostics comes in.
Let's move from power to information then, what the documentation calls the nervous system.
Let's do it.
The sources highlight two main communication protocols, I2C and PCIe. Let's start with I2C. The notes refer to this as the chat protocol.
That's a great way to describe it. I2C, which stands for Inter-Integrated Circuit, is for control, not for heavy data transfer. It uses just two delicate wires, SDA, which is serial data, and SCO, which is serial clock. Think of it as the management channel.
So this is how the CPU tells the little components what to do.
Right. It's the CEO calling the branch managers on the phone. The CPU sends a signal over I2C saying, hey, camera LDO, turn on. Or, hey, ambient light sensor, what's the brightness level in the room right now?
It's a low bandwidth but high reliability conversation.
Exactly.
And the documentation specifically notes that you have to troubleshoot this with an oscilloscope. You can't just use a standard multimeter.
Right, because a multimeter only tells you if there is voltage present. It doesn't tell you if there is actual communication happening.
How does an oscilloscope change that?
With an oscilloscope, you clip onto the line and you physically watch the conversation happen in real time. You're looking for a square wave.
A square wave, like visually on the screen.
Visually, yes. Digital signals are binary zeros and ones. On a graph that looks like a castle wall up, flat down flat, very sharp 90-degree edges, if you see that the line is healthy.
And if it's not healthy?
You see what we call shark fins. The corners are rounded off. That means the signal is physically degrading. Maybe a pull-up resistor has failed. So the CPU is shouting commands perfectly, but the peripherals are just hearing mumbling.
Oh, that makes sense. And that leads to those weird glitches where a phone works, but maybe it randomly restarts every 3 minutes, or the brightness slider suddenly doesn't do anything.
Exactly. The components are there, but they can't understand the boss. But if I2C is the management chat, PCIe is the absolute fire hose.
PCIe, Peripheral Component Interconnect Express. The notes call this the high-speed highway.
This is where the real heavy lifting happens. In an iPhone, PCIe connects the CPU to the two most critical organs, the NAND, which is your main storage, and the baseband, which is your cellular modem.
We aren't talking about simple square waves anymore, are we?
Not even close. We are talking about incredibly sensitive differential pairs carrying gigabytes of data per second.
And the fragility here is terrifying to read about. The notes emphasize that a physical cut or a microscopic fracture in a PCIe line results in an immediate no-boot scenario.
It's entirely catastrophic. If the I2C line to your volume button breaks, you just can't change the volume. It's annoying, but the phone works.
Right.
If the PCIe lane to the NAND breaks the CPU, literally cannot read the operating system. It's like waking up with total amnesia.
So what does the phone do?
The phone will try to turn on. It will show the Apple logo on the screen, but it will just hang there forever because it can't load the basic instructions required to actually be a phone.
It's effectively a lobotomy.
Effectively, yes.
Yes.
And because these high-speed lines run through the inner layers of the logic board, We're talking about a board that is structured like a lasagna with 10 or 12 totally separate layers of copper.
Wait, 10 or 12 layers?
Yeah, so if the board is slightly bent and cracked inside, you often can't fix it. The highway is broken deep underground.
That is wild.
Yeah.
Let's talk about the conductor of this whole orchestra then. We mentioned VDDN earlier, but there's a specific chip that manages all these varying voltages, the PMIC.
The power management IC. The PMIC is truly the unsung hero of the whole device. People assume the battery directly powers the chips. It really doesn't.
Why not?
Because the battery provides a very raw, messy voltage that drops as you use it. It goes from maybe 4.2 volts down to 3.4 volts as it drains. If you fed that directly into the CPU, you'd fry it instantly.
So the PMIC acts like a refinery.
A refinery and a very strict traffic controller. It takes that raw battery power and uses internal buck converters to chop it down into highly stable, precise rails.
Like what kind of rails?
Like exactly 1.8 volts for memory, 0.9 volts for the GPU, 2.7 volts for the camera logic. It manages dozens of these micro power stations simultaneously.
The documentation mentions the boot sequence.
Yeah.
It makes it sound like turning on the phone isn't just a switch flipping, it's a whole cascade.
It's a very rigorous checklist. When you
Yeah.
press the power button, the PMIC wakes up first. It checks, is the
Okay.
battery safe?
Yes.
Okay, turn on the 1.8 volt, always on rail. Is that stable? Yes. Okay, now turn on the DRAM supply.
It literally walks through a sequence.
Step by step. If any one of those rails fails, say there's a short circuit on the display line, the PMIC senses the abnormal surge and immediately cuts power to everything.
It pulls the emergency brake.
Exactly. So very often, a completely dead phone is just a PMIC doing its job perfectly. It's protecting the core system from a short circuit somewhere else on the board.
There's a specific note in the source material here about charging and how the hardware architecture has actually changed from the older Lightning era to the new USB-C era.
This is a massive evolution in how these boards are engineered. In the older iPhones, the Lightning years, there was a dedicated standalone chip near the charge port called TriStar, or sometimes Hydra.
And its whole job was to negotiate with the charger.
Right. Negotiation meaning deciding how much power to safely take in. It would say, hi, I'm an iPhone. I can take 5 watts, or I can take 12 watts.
Okay.
That chip was your first line of defense. If you used a cheap gas station charging cable that accidentally set a huge voltage spike, the TriStar chip would literally burn itself out to save the CPU. It was designed to be a sacrificial lamb.
But now with USB-C.
With USB-C, the protocols are vastly more complex. We have USB Power Delivery, or PD. The control logic for this is often integrated much deeper, sometimes directly into the main system on chip, or a tightly integrated PMIC.
So if you fry the charging logic now...
You might be frying part of the main processor complex itself. The sacrificial lamb is gone.
Oh, wow.
It makes using quality-certified chargers incredibly important. A bad cable can do significantly more expensive damage on a modern architecture than it did 5 years ago.
That is a huge takeaway for everyone listening. Do not use that $2 cable from the bargain bin at the checkout counter.
Never. It's just not worth risking the entire logic board.
Moving on to connectivity. The dreaded no service or searching loop. I feel like this is a very specific panic many of us have experienced. The phone works fine, your app's open, but you just cannot make a call.
This brings us to the baseband section of the board. The baseband is basically an entirely separate computer living inside your phone. It has its own CPU, its own RAM, its own isolated firmware. Its only job is to talk to cell towers.
The notes reference the Qualcomm Snapdragon X65 as an example of this. But what's fascinating is how physical this problem usually turns out to be. The notes mention something called the sandwich.
Ah, yes, the famous sandwich. Since the iPhone X, Apple realized they needed to save horizontal space, so they started stacking 2 logic boards directly on top of each other.
Literally sandwiched together.
Yes, soldered together all the way around the outer rim. The top board usually houses the main CPU. The bottom board usually has the baseband and the Wi-Fi modules.
And if you drop the phone?
The sandwich can physically split apart. The tiny solder pads connecting the top floor to the bottom floor crack.
So the main CPU is working fine. The phone feels totally normal.
But it's screaming down the stairs trying to talk to the modem, and the stairs are completely broken. That's why you see searching forever on the screen. The brain simply can't find the radio.
And troubleshooting this involves checking what the notes call the PMU lines and RF lines.
Right, because even if the sandwich is intact, the baseband is very hungry for power. It needs incredibly precise power delivery, specifically these 1.0 volt and 1.8 volt rails mentioned in the text.
So if the power isn't perfect?
If the power supply ripples even slightly or drops by a fraction of a volt, the modem crashes. It's exceptionally sensitive to dirty power.
Now, this leads us to the part of the documentation that I honestly found the most mind-bending, the section on data preservation.
This is the real core of modern repair.
Because we've talked about hardware up to this point, copper, silicon solder, but there's a ghost in the machine here, the EEPROM.
Right. This is where we leave the world of mechanics and fully enter the world of identity. EEPROM stands for Electrically Erasable Programmable Read-Only Memory.
It's a tiny chip, right?
Very tiny, usually just 8 pins, but it quite literally holds the soul of the logic board.
The notes say it stores calibration data, but reading further, it's not just user settings like your screen brightness or volume. It's way deeper.
Much deeper.
It lists serial numbers, touch calibration camera pairing, battery fuel gauge metrics, Face ID security, and RF tuning.
Let's talk about RF tuning for a second because it perfectly explains why you can't just swap parts around anymore.
Okay.
No two logic boards are physically identical at the atomic level. When they come off the assembly line, there are microscopic natural variances in the copper traces and the silicon.
So kind of like a fingerprint.
Exactly like a fingerprint. So at the factory, they rigorously test the radio on that specific board, and they generate a unique calibration file to perfectly compensate for its specific physical imperfections.
And they save that file in the EEPROM.
Yes. If you lose that chip or if you accidentally wipe that data, the phone permanently forgets how to tune its own radio.
Can't you just download that data from Apple?
No, you cannot. It was generated once, unique to that physical silicon. It's irreplaceable.
This applies to Face ID too, right?
Yeah.
This is the root of the whole serialization controversy we hear about.
It is entirely the root of it. The Face ID sensor and the logic board share a permanent cryptographic handshake. They are paired for life.
So if I break my Face ID sensor and just buy a brand new genuine one from another broken iPhone,
Right.
it won't work.
It will not work. The logic board queries the serial number, sees a mismatch, and permanently disables the security feature.
So for a technician today, this totally changes the entire workflow. You can't just be a mechanic swapping out broken parts.
No, you have to be a data manager. The documentation heavily emphasizes ISP in-system programming.
What does that look like in practice?
Before you even touch a soldering iron to a board, a professional technician connects a specialized programmer directly to specific pinouts on the logic board.
The notes mention tools like JC or Keonly programmers.
Yeah.
Looking at the pictures, they look like little interrogation boxes.
That is exactly what they are. You hook them up to the I2C lines we talked about earlier. You force the memory chip to wake up and talk to you, and you dump the data. You make a secure backup of the EEPROM.
So you're backing up the soul before you operate on the body.
You absolutely have to. Let's say you are doing a complex board swap, like moving the CPU to a donor board because the original fiberglass is cracked in half.
Right.
You also have to physically move that EEPROM chip or securely clone its data over to the new board. If you don't, you might have a technically working phone, but it won't be your phone anymore. Face ID won't work. The battery health won't read correctly. True tone on the display will be totally gone.
Navigating all this requires a map, though. You can't just guess where these chips are or what line does what. The notes talk extensively about board view software.
Board view is non-negotiable. It's not just a flat PDF schematic. It's a fully interactive CAD database of the entire logic board.
How does it work?
You click on a component on your screen, maybe a tiny resistor the size of a dust mote, and the software instantly highlights every single other place on the board that electrically connects to it.
Oh, wow.
It tells you the exact expected voltage, it tells you the signal name, it shows you where the line runs under the surface.
It really is Google Maps for the logic board.
Without it, you are completely flying blind. The traces are buried inside those 12 layers of the board. You can't see them with your eyes. The professional diagnostic checklist in the notes is very strict.
What's the order?
1, measure basic voltages first. 2, check I2C communication with your oscilloscope. 3, check the NAND health via those ISP interrogation boxes. 4, inspect the high-speed PCIe lines.
And then?
Only after all of that data is gathered do you even consider picking up a heat gun to unsolder a chip.
It's the scientific method. It's not just heating things up and hoping to the best.
The heat and hope method is exactly how you destroy the evidence of the real problem. A real engineer measures first.
You know, this deep dive has really shifted my perspective on these devices. We started by saying we weren't going to talk about cracked screens and battery.
Right, the simple stuff.
But when you actually look at the immense physical complexity of the BGA mounting the incredible speed of the PCIe highway, and especially this unique calibration data locked inside the EEPROM, It really makes the device feel much less disposable.
It really challenges the traditional definition of fixing something. We are so used to basic mechanical repair. If a tire's flat on your car, you put on a new tire. The car doesn't care.
The car just drives.
Right. But microelectronics are intricate ecosystems.
It's the difference between a mechanic and a neurosurgeon.
That is exactly it. If you interrupt the blood flow on VDD main, the patient dies. If you sever the nerve on a PCI lane, the patient is paralyzed. And if you lose the memory in the EEPROM, the patient entirely loses their identity.
That identity part is probably the most provocative thought for me to leave with the listeners today. We buy these mass-produced objects, millions of iPhones rolling off an assembly line that look exactly the same on the outside.
Identical metal and glass.
Right. But because of that underlying calibration data, the unique RF tuning, this specific Face ID cryptographic pairing, my iPhone, is actually chemically and digitally distinct from your iPhone.
It is a unique organism at the end of the day. And here's the real philosophical problem for repair. If your logic board dies and that EEPROM is destroyed, that specific phone, that exact unique optimization of hardware and software is gone forever.
It's the ship of Theseus problem, but for the digital age.
Precisely. You can go to the store and buy a new phone. You can store your iCloud backups so your photos are there. But the actual physical entity that was calibrated at the factory to work together in perfect harmony is dead. You haven't fixed it, you've merely replaced it.
That is wild to think about.
It really makes you appreciate the absolute miracle of engineering that happens every single time the phone actually manages to boot up.
Well, on that slightly existential note, I am definitely going to handle my phone a little more carefully today. I
Yeah.
really don't want to crack any of those invisible BGA balls.
Good plan. Gravity is the ultimate enemy of BGA.
Thanks for guiding us through the Silicon City today. It's a truly wild world down there.
Always a pleasure to look under the hood.
And thank you to everyone out there for listening to this deep dive into the hidden architecture of the iPhone. We'll catch you on the next one.